In this video, we're going to show the basic properties of dot product that come straight from the definition. That doesn't include the distributive law, which is going to require more work. But meanwhile, we can get a bunch of properties that we're going to use. The very first one that's listed says if u equals 0, remember that's a 0 vector, or v equals 0 vector, then the dot product must be the 0 number. Now what I'm going to do is just assume that u equals 0, v equals 0, and then try to calculate the dot product. Let's see here. So I'm just going to say, let's calculate the dot product. Remember, the definition is the length of u times the length of v times the cosine of the angle between them. Well, if u equals 0, that's going to say this equals 0. Or if v is a 0 vector, that says this equals 0. In either case, we either get 0 times something or something times 0. In either case, we wind up getting the 0 number, which is really all we wanted to show. So if u is the 0 vector or v equals 0 vector, we calculate the dot product and we get the 0 number. That's the very first thing. The next two properties assume that neither vector is the 0 vector. So how can we write this down? How can I write down that neither u vector nor 0 vector, neither the u vector or the v vector is 0? So we're going to assume, and we can do this in a single statement, and you'll see this a lot in further proofs, but not in this course. If the length of u times the length of v is not 0. That's exactly the same thing as saying both u and v aren't the 0 vector. Yay! Okay, so assuming that neither vector is the unit vector, then we're supposed to show that u is perpendicular to v, and it says if and only if. Now, if and only if has a symbol in mathematics. It's just an arrow with double bars going both ways. So this is going to say u is perpendicular to v if and only if u dot v equals the 0 number. And what I'm going to do is just start on the left-hand side and try to work my way over to the right-hand side with reasoning that goes both ways. So let's write down u is perpendicular to v. We're going to use the trig definition of perpendicular, right? This is going to be if and only if the smallest angle between them, right, is 90 degrees. Like that. All right. That's if and only if the cosine of the smallest angle between them is 0. And now I can multiply both sides by the non-zero length of u, length of v. Since length of u, length of v is not 0, this step is reversible. Right? I mean, I can go from this step to this step by dividing by length of u, length of v. And that's true if and only if. Well, that's the definition of dot product. So u dot v equals the 0 number. And the reasoning goes both ways. So, very often this semester, when we talk about two vectors being perpendicular, we want to automatically go, oh, that means the dot product is 0, and vice versa. If the dot product is 0, the vectors are perpendicular. All right. Next property also assumes that neither vector is the 0 vector. Dot product is trivial if we do the 0 vector. So what they want us to show is that u dot v, is that u is parallel to v. If and only if u dot v is plus or minus the product of the lengths. Now I'm going to start on the left-hand side and see if I can't work my way back. Here we go. U is parallel to V if and only if. Well, again, we're going to use the trig definition of parallel. Two vectors are parallel if the smallest angle between them is 0. Good. Now again, that's going to be true if and only if the cosine of the smallest angle between them is 1 like that. Oop. I want to change this just a little bit. U is parallel to V if and only if theta is 0, or, unfortunately, that angle can be as big as pi. All right, so theta equals 0 or theta equals pi. That's better. That's going to say the cosine of theta is plus or minus 1. Better. Now what I want to do is multiply both sides by the non-zero length of U, length of V. This is going to be length of U. Better. Length of V. Cosine of the angle between them equals plus or minus the length of U, length of V. Like that. And we did this so we actually put a dot product in here. This is length of U, length of V equals plus or minus the length of U, length of V. Like that. You notice, by the way, if the angle's small enough, right, this says that the dot product looks just like the products of their lengths. So in that sense, it feels like a product. All right, what's the next one? The next one is stuff that we use a lot, but is now trivial, but we need to write them down once. The next thing we're supposed to show is that, oops, I dot I equals J dot J, and little arrows over here, equals K dot K, like that, equals 1. Let's just do I dot I. The others are exactly the same. If I want I dot I, that's supposed to be the length of I times, remember this is just ordinary multiplication, length of I times the cosine of the angle between I and I, but theta equals 0 here, so the cosine of theta equals 1, and I is defined to be a unit vector, so this is 1, and this is 1, times the cosine of the angle between them, which is also 1, and so we get that I dot I is 1. The reasoning is just exactly the same for J dot J and K dot K. So actually this is true for any vector, any unit vector. The next thing they want is I dot J is equal to J dot K equals K dot I. What do we want here? One word about notation. If you want to write I and J with hats, that's perfectly fine, but never leave the arrow or the hat off. Just a reminder of what I, J, and K are. I is defined to be the unit vector that goes in this direction. J is defined to be the unit vector that's 90 degrees counterclockwise of that, and then K is defined to be the unit vector that's 90 degrees counterclockwise in that, right? And so they're defined actually to all be perpendicular to each other. Now once we actually say that they're defined to be perpendicular to each other, then I dot J must be 0, and J dot K must be 0, and K dot I must be 0, so we get 0. Without breaking too much of a sweat. Another thing that gets used a lot, and is really nothing new if you actually look at this, it says that for any vector, V dot V is the length of the vector squared. And And it really looks like v times v is equal to v squared. It's not quite the same, but how would we show this? Well, let's just calculate it. V dot v is the length of v, ordinary multiplied by length of v, times the cosine of the smallest angle between v and v. Well, the smallest angle between v and v would be 0. Let's just write this down here. And then the cosine of that angle equals 1. And so what we're going to get is the length of v times the length of v. Well, that's just the length of v squared. And that's it. It wasn't so bad, but this gets used a lot, so don't forget it. The next one says u dot v is equal to v dot u. Now, what you're going to hear a lot is they'll say dot product is commutative. This is what we mean when we say dot product is commutative. It shouldn't mean anything. Let's just write down the left-hand side definition. It should be the length of u times the ordinary multiplication times length of v times the cosine of the smallest angle between them. Well, that's actually the important part here, right? So if someone draws any vector u and any vector v, yes, the smallest angle between them is this angle. It doesn't matter if we phrase it first by saying the smallest angle between u and v, or the smallest angle between v and u. What we're really saying is that theta actually has to be a positive angle, right? And that just doesn't depend on whether u comes first or v comes first. Since this doesn't depend on whether v comes first or u comes first, we're going to actually just get the other dot product. Because ordinary multiplication, well, let's write it this way. This will make me feel better, right? Equals this. Ordinary multiplication is commutative. And now I can say that theta doesn't depend on which comes first. It doesn't care which one comes first. This should be v dot u. And now I did a better job of actually just writing that out formally. All right, that's all the basic properties of dot product that we're going to use outside of one. And the other one I think is actually easier once we get the formula. It's very intuitive, but I don't want to do it now. All right, on to the distributive law.